Hi, in this video, we will discuss about the background for the Laplace transform. Before we continue on Laplace transform, let's recall what kind of transform you have learned so far. So you should have learned how to transform between the rectangular coordinate to the polar coordinate. So for example, in this case you have a complex number, x equal to a plus bi, where your a is the real number, b is the imaginary number. So let x to be 5 plus 6i. So if we draw this on the 2D graph, where the x-axis is the real part and the y-axis is the imaginary part, so x equal to 5 plus 6i is located here, this point, where your x, real part is 5 and your imaginary part, is 6i. So this is the rectangular coordinate, or what we call Cartesian coordinate, is the same thing, where you can find the real part and also the imaginary part. Besides represent this point by using the rectangular coordinate, we can also use the polar coordinate. So let's say we have the magnitude here. So the magnitude can be found by using this equation, which is approximate to 7.8. And also you need to know the phase. So the phase here, by using the triangle, we can know that the angle is equal to inverse tangent 6 divided by 5. So you can see the length here 6 divided by 5, you get tangent angle here. And after calculation, you get around 0.88 radian, and you can convert to degree by multiply this 0.88 multiplied with 180 divided by pi, then you should get around 50 degrees. So since it's in first quadrant, so your phase will be equal to 50 degrees. So by knowing the magnitude and also the phase, we can know the location for the point. So this is known as polar coordinate. So this is the formula that we use to find the magnitude and the phase, and we success to obtain the magnitude equal to 7.8 and your phase equal to 50 degrees. So when you substitute inside, then you get the polar form like this. We also can convert from the polar to the rectangular coordinate by using this formula. So if you substitute the magnitude and phase inside this formula, you should be able to obtain the real part, 7.8 cos 50 degrees, you should get approximate 5. And if you take 7.8 sin 50 degrees, then you should get the imaginary part, which is approximate to 6. So this is the coordinate transformation that you have learned previously. We can also represent the polar coordinate into this form, where we can use the Euler formula exponential I angle equal to cos angle plus I sin angle. So we also can represent the x equal to 7.8 exponential I 50 degrees. So this is also one of the polar forms. You should familiar yourself with the coordinate transformation because this is very important. So for the first example, if you have a complex number equal to 3 plus 4i, the real part is 3 and the imaginary part is 4. So you should be able to draw the 2D graph, which is located in the first quadrant here. So by using the formula, you should be able to obtain the magnitude equal to 5 and the angle equal to 53 degrees. So since this is first quadrant, so your angle here is 53. So for the next case, negative 3 plus 4i. So in this case, your real part is in negative 3. So your y is positive. Okay, so you should get the triangle in second quadrant. So the magnitude is still remains 5, but in this case, you compute the angle in the second quadrant. So to know the angle, okay, from here, from the 0 degree here, which is the x-axis, to the point here, so this angle is equal to 180 minus with the 53 degrees. So with that, you should be able to obtain the angle to be 126.87. So let's continue. For the next case, you have negative 3 minus 4i. So the real part is negative 3 plus imaginary part negative 4, going down. So this is at third quadrant. So if you compute the angle, you will get the angle 53. To calculate the actual angle, so it will be 180 plus 53, which is 233. Lastly, you have 3 minus 4i. So if you draw it, you obtain 3 positive, negative 4. So this is the fourth quadrant. So same, if you compute the angle, you get the angle 53 for this triangle. But the actual angle should be count from the x-axis, which is from here to this point. So the angle is 360 minus with the angle. With that, you obtain 306.87 degrees. So you have to consider the quadrant to compute the actual angle. So far we have discussed how to convert from rectangular to polar or from polar to rectangular. So this is known as coordinate transformation. So why we perform the transformation like this? As you can see in the rectangular coordinate, you can obtain the important information such as the real part and also the imaginary part. On the other hand, for the polar coordinate, you can obtain the magnitude and also the phase directly from this domain. So you can see that you can obtain important information from different domains. In simple, you can only obtain certain information in one particular domain. For example, you can only obtain the real number and imaginary number in the rectangular coordinate. But if you perform the transformation and transform it into the polar coordinate, you can obtain new insight or new view about the new information, such as the magnitude and phase in this new domain. So this is the importance of doing transformation. Fourier transform and Laplace transform are two important transformations in the engineering application. So this is the equation for the Fourier transform, which is in the improper integral format, where you need to integrate from negative infinity to the infinity. The time domain function ft is multiplied with the exponential function here. And by doing this, you're able to convert the time domain ft into the frequency domain. Let's say we have a sine wave and we would like to convert it into the frequency domain. In this case, we can just use the formula frequency equal to 1 over period. So if we know the period here, let's say the period is 5 seconds for one cycle. So we can substitute, we get 1 over 5 to be the frequency. So in the frequency domain, you should be able to see at 1/5 Hz here, there is one peak, indicating that this sine wave consists of frequency equal to 1/5. In this case, our ft is a complicated waveform where it is hard to determine the frequency content in this waveform by using the previous formula f equal to 1/t. We can still find the frequency component by using the Fourier transform. And this is the result. You can see there are 5 peaks indicating 5 frequency components from low frequency to high frequency here. So in general, Fourier transform is very useful to convert a signal from time domain to frequency domain. So in the time domain, it's hardly to tell what is the frequency component contained inside the signal. But by using the Fourier transform, the frequency component can be easily found here. If we check the previous equation here, you found that the original time domain signal ft is multiplied with the exponential with negative I omega t. So the exponential term here basically is used to find the steady state behavior of the signal, which is in this case is the frequency content omega. On the other hand, we have the Laplace transform equation here, where you can see the equation is almost similar to the Fourier transform, where you have the ft multiplied with the exponential negative I omega t, which is used to extract the frequency content from the ft. So you have additional term exponential negative sigma t, where sigma normally indicating the decay or the growth rate. So this is to extract the decay or growth component from the ft as well. In general, exponential negative I omega t is to find the steady state behavior, which is the frequency content, while the exponential negative I negative sigma t is to find the transient behavior, which is the decay or growth rate. So we are looking for two components. In the real part, we are looking for the sigma, and in the imaginary part, we are looking for the frequency. So this is known as the complex frequency signal, which is written in the form of x. Substitute the x into the formula, then you will get this equation, where you can see the exponential is simplified into x only. So we can say that our time domain signal ft, by using the Laplace transform, it can be converted to capital Fx. So the time domain signal is converted to the x domain signal. And what is x domain? X domain is equal to sigma plus I omega, and this is complex frequency signal. So complex frequency have two components. In the real part, you have the growth or decay rate, and in the imaginary part, you have the frequency. In this study, our main focus is the Laplace transform, but at least you should know the relationship between Fourier transform and Laplace transform. So when we let the x equal to I omega, where the decay or the growth rate is equal to 0, then in this case, we can convert the Laplace transform to the Fourier transform. So this is the relationship, where you can see when your x equal to I omega, your sigma will be equal to 0. And by that, this term can be cancelled and you get the Fourier transform. You must know what is cursor and what is linear system. So for a linear system, it must obey the superposition law. So we have a system here where your input excite the system to give the output. Let's say we have the cantilever beam as the system, and we excite the system by using the motor rotation force here. So as the result, the beam will experience vibration. In the first scenario, let's say our motor input force is equal to 5 sine 2t. So when we excite the system, the vibration is 10 sine 2t. In the second scenario, let's say we have the second motor excite the system at 5 sine 10t, and the output that we obtain is 3 sine 10t. Can you predict what if we run two motors simultaneously? Can you predict what is the output due to these two motors? In engineering application, if a system is linear, then we can apply the superposition law. So in this case, we have the input 1 and input 2 acting simultaneously to the system. Then the total output will be equal to the summation or superposition of output 1 plus output 2. In engineering application, most of the system will be Causal. So what does this mean? So it means that without any input, our output will be 0. So let's say your force here is equal to 0. Then you should get your response equal to 0 as well. Because there is no force acting on the system, therefore no response due to the force. In graphical, you can imagine that you have 0 force when t is less than 0. Therefore, the response before t equal to 0, here, it will be 0 as well. So, let's say at t equal to 3, you start to apply the impact force. And for the response, you should expect that at t equal to 3, you will occur the corresponding response. So this is known as Causal system. And if you measure the response at point far away from the force, then you may capture the response at t greater than 3. Let's say at t equals 5 here. So after some delay, only the vibration reaches to that point. By that, only you receive the response. So this is also known as Causal system, where you see the response occur after the impact force. If you have the response occur before the impact force like this, it doesn't make sense to you, right? Where before the impact happens, you have the response. So this is non-Causal system, which is not covered in physical system. We only deal with Causal system in our case, where your response occurs only after you give the impact. For a Causal system, your Ft will be equal to 0 when t is negative or when t is less than 0. So this is the equation for the Laplace transform. Considering the linear and Causal system, we can simplify it into this equation, where you can see integration, you can separate into negative infinity part to 0 plus 0 to infinity. So for the negative infinity to 0 part is this component, where you know that when t, delta t, where your limit when t is less than 0, you know that your force is 0 as well. So when you substitute this to be 0, when you integrate, you should get 0. So therefore, this component can be equal to 0, and eventually you only get this. So later, you will find that we will compute the Laplace transform by using this equation instead of this. And there is a name for this. So we call this as unilateral, and this is bilateral. So you can see bilateral Laplace transform we perform in two sides. Okay, one side is negative infinity to 0, another side is 0 to infinity. Well, the unilateral Laplace transform is transformed in one side only, which is 0 to infinity. This is the focus of the study. So after perform Laplace transform, you should be able to obtain the signal or data in the S domain. And you should know X is the complex frequency, which is equal to sigma plus I omega. So from the X domain, we can obtain useful information like the pole and the zero. Pole is the X that causes the zero denominator, and what is zero? Zero is the X that causes the zero denominator. So in simple, you want to find what is the X, okay, when you get the value at the bottom should be 0. Well, the 0 is the X where you get the value at the top to be 0. So you can see that you have one pole here, because when you let X equal to negative 1, substitute you get 0 at the bottom. So with that, you can say that this is the pole. The pole is X equal to negative 1. And you cannot let any value of X that costs 0 at the top. So with that, we say we don't have 0 in this case. By using the same method, you can see that you have 3 poles for the second case, where X equal to negative 1 here. And from here you get your root to be X equal to negative 5 plus minus 2i. And we don't have the 0 because no X can be made so that it gets 0 at the top. So we have the third case here with the same poles, because the denominator is the same. At the top now, instead of 1, it's now become X minus 2 multiplied with X plus 2. So when you let X equal to 2 and X equal to negative 2, you will get 0 at the top. So you have 2 zeros here, which is these two X. So normally poles is indicated by the symbol X, and the 0 is indicated by the symbol 0. So if you want to sketch the S domain, you can draw the 2D plot like this, where the sigma is the real and I omega is the imaginary. So for the first case, you have the pole X equal to negative 1 and your X equal to sigma plus I omega. So this is equal to negative 1. So since your I here, you have nothing. So when we compare, we know that your sigma is equal to negative 1 and your omega equal to 0. So with that, omega equal to 0, sigma equal to negative 1. And here, you should draw X. So this is the plot for the first case. So let's look at the second case. Second case, you have 3 poles and without 0. So S equal to negative 1. So you have the pole here. So another 2 poles at negative 5 here, and plus 2 to be here, and negative 2 to be here. So in total, these are the 3 poles. Let's look at the third case. So you have the same 3 poles here, which is this, and you have 2 zeros at 2 and negative 2. So for the 0, we indicate by the O or 0 here. So this is how we sketch the data in Laplace domain. In the Laplace transform, we are going to use the mathematical technique such as the integration technique, partial fraction technique, factoring, completing the square, as well as solving the improper integral. So this, you should have learned this in the engineering mathematics 1. So please recall this